Hello and welcome. Today we're doing a question from LeetCode called Coin Change. It is a medium. Let's get right into it. You are given an integer array coins representing coins of different denominations and an integer amount representing a total amount of money. Return the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combination of the coins, return -1. You may assume that you have an infinite number of each kind of coin. Example 1, we're given coins 1, 2, 5 and amount 11. Here we output 3 because we take 1, 5, a second 5, and 1, 1 to make 11. And again, we have an infinite number of each coin, so we can use as many as 1s, 2s, and 5s as we want. Example 2, coins 2, amount 3. No amount of 2s will sum up to 3, so we return -1. Example 3, coins 1, amount 0. Here we don't return -1, we return 0 because to make amount 0, we need 0 coins and we can make that figure, and which is why we return 0. Example 4, coins 1, amount 1. We just need to use 1 coin of 1 to get 1, and 5, coins 1, amount 2. Use 2 of the 1s to get to 2. Now, this is similar to something called a knapsack problem, which basically means there's no real shortcut or trick to it. We need to figure out all the different combinations to get our answer. And this is because we can't predict what coins are going to be used in our final answer. For example, we can't approach it in a way saying, hey, let's try using the largest coins we have, and we can't use those anymore, try smaller ones. Because what if we had the following example, coins 3, 11, amount 21. We try to use 11, and now our remaining amount would be 10, but neither 3 nor 11 can actually get us to 10, so that approach won't work. We'll actually have to be using 7 of the 3 coins to get to 21. Something we can do, however, is keep track of our previous calculations and use them for future ones. This is called memoization, which can be done through dynamic programming. But before we solve it iteratively, let's take a brief look at another approach. We're going to solve this recursively and look at it from top down very quickly before we move on to our iterative solution. So like always, the very first thing we want to do is start off with an example. Here I have an example where coins are 1, 2, 5, and amount is 6. What is the minimum number of coins needed to make amount 6? Well, we have coins 1 to 5 at our disposal. What we want to do is try out all the ways to make 6 from these coins and use the way that uses the least number of coins. So first what we can do is try out using coin 1. We have amount 6 and we use coin 1, we're left with amount 5. This means if the minimum number of coins needed to make 5 is x, it takes x plus 1 to make 6. It will take at most x plus 1 coins to make amount 6. Now, instead, if we try using coin 2, we're left with amount 4. And if y is the minimum number of coins needed to make 4, it will take at most y plus 1 coin to make amount 6. It only takes 1 coin to go from 4 to 6, only takes 1 coin to go from 5 to 6. And here in this visualization, every level difference is representing an additional coin being used, while each coin is being represented by a slash and the denomination that it has. So here we use a single coin valued 1, a single coin valued 2. Moving on, if unless using coin 1, coin 2, we decide to use coin 5, our amount left would be 1. And if z is the minimum number of coins needed to make that amount, it would take at most z plus 1 to make amount 6. So from all of these, right, from 5, 4, 1, it only takes 1 additional coin to get to 6. Just takes 1 more coin valued 1, 2, or 5. So what do we want to do here? We want to find the minimum number of coins needed to make the remaining amount. The coins needed to make 5, 4, 1. So that is x, y, z. What we want to do is have 6 equal the minimum of x, y, z, and just add 1 to that. And that's how we know the minimum number of coins needed to make 6. But now, how do we figure out what x, y, z are? We can do the same thing. We can just use all the coins on each of them and go all the way down, bubble back up, and find out what 6 is. However, with this, we would be doing a lot of repeat operations. So instead, what we want to do is use the smallest coin we have and go as far down as we can. Once we do that, then move on to the bigger coins such as 2, 5. This way, we'll store all these computations in something called Memo. It's going to be a dictionary holding the amounts and the minimum number of coins needed for said amount. And as we move on to the bigger coins, we'll just update Memo since our smaller calculations have been complete. So let's walk through all of this, right? The first thing we do, we have amount 6. We start off with coin 1. It's our smallest coin. Now we have amount 5. So again, this is a new problem. We have amount 5, coins 1, 2, 5. We want to use the smallest coin we have, coin 1. We're at amount 4. What is the smallest number of coins needed to make this amount? We have no idea. We don't even know if we can make amount 4 yet. So as a placeholder for all of these amounts, we're going to say it takes infinity as the minimum number of coins needed to make these amounts. And I will explain why we use infinity in a little bit. Anyways, we are at amount 4. We want to use the smallest coin, which is coin 1. Now we're at amount 3. Amount 3 is the smallest coin, which is 1. We're at amount 2. And you can see this is how the recursive stack is being built, right? We can't return to 3 until we finish with the call from 2. So at 2, go with the smallest coin, we're at 1. Smallest coin, we're at 0. At amount 0, we've seen this before. It takes 0 coins to make 0. So this is something that's actually also going to be stored in Memo. The keys here are going to represent amounts. Values are going to be the minimum number of coins needed to make said amount. So it takes 0 coins to make 0, and we know that. So here, the x for this would just be 0. It takes 0 coins to make amount 0. Let's try using coin 2. Now we move up, right? We started off with the smallest, now we go on to the next ones. We're going to loop through all these coins. However, we can't actually use coin 2 because it's greater than the amount we're currently on. It wouldn't make sense, we'll be left in a negative value, so move on. Try 5, again, there's no need to continue. We've already gone past the amount we need. 5 is greater than 1. So here, the minimum of x, y, z would just be x since there is no y, z, and we know it's 0. All we have to do is add 1 to that to go from 0 to 1, and now we have the smallest number of coins needed to make amount 1, and we can add it to Memo. So this would be 1. And we can now return back to 1's caller, which is 2. So again, as mentioned earlier, we're going to set everything min coins needed to infinity. We don't even know if we can make 2 yet, but once 1 returns, we know the minimum number of coins needed after we use a single coin is 1. And every time a branch returns, we'll just update min coins needed accordingly. So essentially, min coins needed is equivalent to the min of x, y, z. So now we try with coin 2. The amount remaining would be 0. 2 minus 2 is 0. And we want to check in Memo. It does exist, so we know it would take 0 more coins to make the remaining amount. We update min coins needed to be 0. And now we try coin 5, but there's no point in continuing. It's greater than the amount we have. So here, what's the minimum, right? It's just x, y, there's no z. It's 0, which we have in min coins. All we have to do is add 1 to this. It takes 1 coin to go from 0 to 2, and that's a coin value 2. And we can add this to Memo. 1 coin to make 2. And now we pop back up to 3. So again, 3, the min coins needed is set to infinity until 2 returns with its value of 1. Once it does, then we update min coins needed to be 1. And we try coin 2. Amount is 1. Checking Memo. Value is 1. And check 5, we know we can't continue. So they're going to be sort of 2 stop cases for our recursive solution. 1, if the coin we're on is greater than the amount we're on. And if the amount we are looking for already exists in Memo, we just return the number of coins needed to make up that amount. So here, min coins needed is 1. Add 1 and add that to our Memo. So 1 plus 1 is 2. It takes 2 coins to make amount 3. And once we return to 4, after 3 also returns, we know the min coins needed right now is 2 after we've solved for branch 1. Now let's try branch 2. So we use coin 2, and we're left with amount 2. Checking Memo, it takes 1 coin to make 2. Update min coins needed. Try 5, there's no point, it's greater than 4. So we're done, we finished this loop. All we have to do is add 1 to min coins needed, and update memo. So now once we've popped back up to 5, min coins needed from infinity changes to 2. It takes 2 coins to make the remaining amount after using coin 1. If we try using coin 2, we are left with amount 3. Takes 2 coins to make that, no need to update min coins. And after using coin 5, we have amount left of 0. Check in memo, takes 0 coins to make that. Update min coins needed. We've completely gone through all the coins we have at our disposal. Add 1 to min coins needed and add that to memo. So it takes 1 coin to make 5. And now we pop back up to 6. So we know x is equivalent to 1 and min coins would be 1. Now we try branch 2. So coin 2, we're left with amount 4. We've seen this in memo. And this is what it means to not repeat calculations, right? We've done and computed 4 already, so all we have to do is look it up. We know it takes 2 coins to make amount 4. No need to update min coins needed. For coin 5, we're left with amount 1, and it takes 1 coin to make that. So min coins needed would stay 1. The minimum of all of these is 1, which we have stored in min coins needed. All we have to do is add 1 and add this to memo. So to make amount 6, we need a minimum of 2 coins. That's the smallest number of coins that will get us amount 6. Now let's look at one quick example, and this is going to describe why we want to set everything to infinity initially. If we have coins 2, amount 3, everything initially set to min coins as infinity, right? And our memo would hold 0, 0. So we're at amount 3, we use the smallest coin, which is 2. We're at amount 1. Here, we can't really use 2 because it's greater than our amount, so we return. And remember, min coins was infinity. So here, all we're going to do, add to memo, we're not going to add 1. If it's infinity, all we do is add infinity as our value. And we pop back up. All the branches here return infinity, and the minimum is going to stay infinity for that. So for 3 as well, it's going to be infinity. This is how we know we actually can't make up that amount. No amount of combinations will actually get us that amount, and we would return -1 if we see infinity as a value for our amount. So let's go ahead and code all of this up. First thing we're going to do is initialize self.memo. This is a dictionary where the keys are going to be amounts and the values are going to be the minimum number of coins needed for said amount. And we know right away it takes 0 coins to make amount 0. If you notice something else, all the coins that we have, those following amounts, so 1, 2, 5, it only takes 1 coin to make those amounts. Of course, we just need 1 of that coin itself. So what we can actually do is go through and add that to our memo as well. So for coin in coins, if coin less than equal to amount, there's no need to add it otherwise. Self.memo of coin equals 1. Now what we want to do is sort the coins in ascending order. We always want to start with the smallest first and then work our way up. And we're actually going to call a helper function. So value is going to be self.helper on coins, these sorted coins, and amount. Once that returns, we're going to return that value. So the number of coins needed to make amount. Return value if value not equal to float infinity. Else we return -1, indicating we actually can't make up that amount. And now we work on the helper, the core of our logic. So helper self coins amount. What's our base case? If amount in self.memo. If that is the case, we just return the number of coins needed to make that amount. Now we go ahead and set min coins needed to infinity. And we're going to loop through all the coins. For coin in coins, if coin less than equal to amount, no point in continuing otherwise, coins needed is equal to self.helper coins amount minus coin. So if we start off from 6, right? The first coin we use is 1. We're in this for loop. We're in coins needed. we call helper on all the coins we have, and amount minus coin, indicating we're using this coin. So our new amount that helper is going to be passed in with is 5. And once that returns, we're going to update min coins needed. So min coins needed is going to be the minimum of what's there currently and what this branch returns. Remember, every time a branch returns, we update min coins needed. And once we are out of this for loop, once we have tested out all the branches, all we have to do is check if it's infinity or not. So if min coins needed is equal to float infinity, and this also should be float over here, we add 1 to min coins needed. And why are we doing this? We now have our minimum here. We just have to add 1 and add that to memo. So self.memo of amount will be min coins needed. It should be not equal to infinity, then we add 1. If it isn't equal to infinity, we don't add 1 and simply add infinity to memo with this current amount. And finally, all we have to do is return min coins needed. So let's go ahead and run this code. Wrong answer. Let's see what happened here. We forgot to return. So let's go ahead and run this code. Accepted and submit. And it is accepted as well. So let's do a super quick walkthrough of this code before talking about time complexities. If we have the example coins 1 to amount 3, based on this, self.memo is set, has 0, all the coins have values 1. We call helper after sorting, which they're in sorted order anyway. So in helper, amount is 3. We don't have this in memo, set min coins needed to infinity, start with coin 1, coins needed, can't return until we call it with amount 3 minus coin, which is 2. So we're in new call stack. Here, this is in memo, so all we have to do is return 1. So coins needed becomes 1. We update min coins needed from infinity to 1 and move on to coin 2 for the next one in the for loop. So with that, amount now becomes 3 minus 2, which is 1. It also exists in the dictionary, so all we have to do is return. Coins needed is 1. We don't need to update min coins, it's already what it is. Since it's not equal to infinity, add 1 to it, so it becomes 2, and add that to memo. So 3 will now have 2. So this is how this code is running. Finally, value would return, and we would return 2. Now for this time complexity, theoretically for every single amount, we have to go through every single coin. So if the coin's input is n, and let's say amount is m, the time complexity would be O of m times n. And that is it for the recursive solution. Now we are going to be solving this iteratively, so the exact opposite of what we did before. Before we started from amount and went down until we hit 0. Now we're going to start from 0 and work up until we hit amount. If you want to pause this video, give it a shot, feel free to. If not, we're going to jump in and get started. So here, instead of using memo, we're going to make use of a DP array, where the indices are going to represent our amounts, and the value at those indices is going to be the minimum number of coins needed to make that amount. In the beginning, our DP array is going to look something like this for the same example as before. We have indices 0 to 6 representing amounts, and coins needed is set to infinity. We don't know if we can make those amounts yet. So let's go ahead and start coding this. For I in range amount plus 1, because this is not inclusive, dp.append float infinity. So we have the following DP array right now from 0 to 6. However, we know at 0, it only takes 0 coins to make, and we can update that. To make amount 0, it's only going to take 0 coins. All we have to do now is loop through all the amounts. So for amount in range 1 amount plus 1, we want to start from amount 1 up until 6 because we already know what's at 0. Now we loop through all the coins. So for coin in coins, if coin less than equal to amount, the index we're on, only then do we want to continue. And we can go ahead and update DP to be the minimum of coin or what's there right now. So DP amount equals minimum of what's there right now. And what happens if we actually make use of this coin? So amount minus coin plus 1. If we make use of this coin, we have to add a plus 1. And if we want to subtract that amount, we want to look up in DP. So for this amount, the minimum number of coins needed. And we just add 1 to that to get our final answer. And after we are out of this for loop, all we have to do is return. So we return DP of the original amount if DP of original amount not equal to float infinity, and that means it exists, else we return -1, signifying we can't make this amount. Let's do a quick walkthrough. So we ended at line 9 after we updated 0 in our DP. Now we are at amount 1. And let's say we start at coin 1 for coins 1 to 5. 1 is less than or equal to 1. We go into line 13. DP of amount is currently infinity. And amount minus coin. So 1 minus 1 is 0. So what is at index 0? How many coins are needed to make 0? So at 0 is value 0. So 0 plus 1 is 1, and we can go ahead and update DP because that is less than infinity. And now we are out of this loop. Try the other coins 2 and 5, but we know they're going to fail in this if condition. So we go out, and now we are in amount 2. Try all the coins 1 to 5. Start with 1. DP 2 minus 1 is 1. What's in 1 right now? 1. 1 plus 1 is 2. So we can go ahead and update this because this is the new minimum. We're back in this for loop. Let's try coin 2. 2 is less than or equal to 2. Amount 2 minus coin 2 is 0. What's at index 0? Value 0. 0 plus 1 is 1. We can go ahead and update DP amount to be 1. It only takes 1 coin to make amount 2. And in this manner, we're going to go through and update all of our indices up until we hit amount and finally return what's in the last amount. We're going to return -1 if it's infinity or the number that is there. Time complexity for this is going to be the same as before, O of n times m. For every single amount, we're going to go through every single coin. And for space, it is going to be O of m, where m is going to be the amount. We have values for 0 up until amount, so it's going to be O of m. Let's try running this code. Accepted and submit. And it is accepted as well. If you have any questions, let me know down below. Otherwise, I will see you next time.